Look up at the night sky, and you're gazing into a seemingly peaceful ocean of stars, calm, timeless, and undisturbed. But that tranquility is an illusion. Out there, in the deep reaches of space, titanic forces are at work, collisions between galaxies so immense, so powerful, that they reshape the cosmos itself. Imagine two galaxies, each home to hundreds of billions of stars, slowly drifting toward one another over millions of years, drawn together by the relentless pull of gravity. What unfolds is not just a crash, but a breathtakingly beautiful and violent dance of creation and destruction, one that births new stars, awakens sleeping black holes, and forges entirely new worlds. For decades, astronomers believed these galactic collisions were rare cosmic accidents, but today, we know they are anything but rare. They are fundamental, inevitable, and essential to how galaxies live, evolve, and die. In fact, our own Milky Way is no stranger to this process. It has consumed smaller galaxies throughout its history, and in about 4.5 billion years, it too will collide with the Andromeda Galaxy in an event that will forever alter the night sky as we know it. These aren't just distant curiosities, they are the engines of cosmic evolution, and they hold secrets that challenge our deepest understandings of space, time, and existence. In this video, we're going to explore 20 shocking revelations about galactic collisions discoveries that rewrite the rules of astrophysics and reveal a universe far more dynamic and creative than we ever imagined. From starbursts that ignite thousands of new suns in an instant, to the merging of supermassive black holes that send ripples through the fabric of space-time, each revelation pulls back the curtain on a process that is both destructive and profoundly generative. This is a journey to the heart of how galaxies are born, how they grow, and how, in their most violent encounters, they give rise to the conditions that make life possible. So settle in, open your mind, and prepare to see the cosmos in a whole new light. Picture our own cosmic neighborhood, the Milky Way. It appears as a majestic, swirling disk of stars, a seemingly isolated island in the vast ocean of space. But this peaceful image is a facade. We are, in fact, living within a predator. Our galaxy is a cannibal, and it is currently in the process of devouring a smaller companion. This is the shocking reality of galactic cannibalism, a process far more violent and transformative than a simple merger. It's not a meeting of equals but a systematic dismantling, where a larger galaxy uses its immense gravitational pull to tear apart a smaller one, stripping it of its stars, its gas, and even its dark matter over billions of years. The evidence is written across our own night sky. Astronomers have mapped vast, faint rivers of stars that arc over the poles of the Earth, celestial streams that are not part of the Milky Way's main disk. These are the tidal tails of the Sagittarius dwarf spheroidal galaxy, a tiny satellite galaxy that has been caught in our galaxy's gravitational grip and is being slowly, methodically ripped apart. Its stars are being pulled out into long ribbons, eventually to be absorbed and assimilated into the halo of the Milky Way. This isn't some ancient, concluded event. It is happening right now above our heads, a silent, cosmic feast playing out in ultra-slow motion. This process of assimilation is anything but gentle. As the smaller galaxy is shredded, its gas clouds are violently compressed and driven inward toward the heart of the larger galaxy. This sudden influx of fresh fuel can ignite ferocious waves of new star formation, lighting up the galactic core. In even more extreme cases, vast quantities of gas can be funneled directly into the supermassive black hole that lurks at the center of most large galaxies. When this happens, the black hole awakens from its slumber, transforming into an incredibly luminous quasar, an active galactic nucleus that can outshine every star in the galaxy combined. So, cannibalism doesn't just change a galaxy's structure, it can fundamentally alter its energy output and evolutionary path. Perhaps the most humbling realization is that the Milky Way is not unique in this behavior, it is the cosmic norm. Our galaxy is a seasoned predator with a history stretching back billions of years. Studies of the motions and compositions of stars in our galactic halo reveal that they are the remnants of dozens of smaller galaxies that our Milky Way has already consumed. Each of these ancient mergers has left its mark, contributing stars and shaping the galaxy we see today. This means the very ground beneath our feet, the atoms that make up our planet and our bodies, were likely forged inside stars that originated in different, now devoured dwarf galaxies, all brought together by this relentless gravitational dance. But if galactic cannibalism shows us the visible violence of these encounters, the second revelation takes us into the invisible realm, forcing us to confront a fundamental truth about the universe. Most of it is made of something we cannot see. This is the mysterious role of dark matter. During a galactic collision, everything we expect to happen based on the behavior of stars and gas is turned upside down because dark matter doesn't play by the same rules. Unlike normal matter, dark matter doesn't interact with electromagnetic forces. It doesn't collide, it doesn't compress, and it doesn't emit any light. It is, for all intents and purposes, a ghostly presence that only makes itself known through its immense gravitational pull. This leads to one of the most counterintuitive and shocking outcomes of a galactic collision, a separation of the seen and the unseen. Imagine two galaxies flying toward each other at millions of miles per hour. When they meet, their clouds of interstellar gas will slam together, creating immense shock waves and heating up to incredible temperatures. Their stars, while unlikely to physically collide due to the vast distances between them, will be gravitationally whipped into new orbits, forming dazzling tidal tails. But their halos of dark matter, they simply pass right through one another, like two ghosts walking through the same wall without a sound. The gravitational aftermath of this event is what reveals the truth. The most famous and compelling evidence for this comes from observations of an object known as the bullet cluster. This isn't a single galaxy, but actually two galaxy clusters that have recently collided in one of the most energetic events ever recorded in the universe. By carefully mapping this system, astronomers could pinpoint the location of the total mass, mostly dark matter, using the way its gravity warps the light from more distant galaxies, an effect called gravitational lensing. They could also map the location of the hot gas, which is filled with normal matter, by detecting its X-ray emissions. The results were staggering. The two maps did not line up. The clouds of hot gas, slowed by the collision, lagged behind, but the dark matter, completely unaffected by the impact, had sailed ahead of the gas, taking the majority of the mass with it. This was a direct, observational proof that most of the matter in the universe is dark and behaves in a way that utterly defies our everyday experience. This revelation forces a complete rethink of what a galaxy even is. We are not living inside a simple disk of stars. We are living deep within an enormous, invisible sphere of dark matter, a halo that is far larger and more massive than all the visible stars, gas, and dust combined. It is this dark matter halo that provides the gravitational scaffolding upon which the visible galaxy is built, and that dictates its ultimate fate during a collision. The stars and gas are just the visible traces, the flotsam and jetsam caught in the irresistible gravitational currents created by these unseen giants. Understanding this invisible architecture is absolutely key to mapping the true, hidden structure of the cosmos and finally answering the question of what holds it all together. Yet out of this violent chaos emerges one of the most beautiful and creative processes in the universe. While the dark matter halos pass through one another and the gravitational tides tear stars from their orbits, the clouds of gas and dust within the galaxies do not have the same ghostly luxury. They are tangible, and when they collide, they behave just like any other matter. They slam together. This brings us to our third shocking revelation, a phenomenon where destruction gives birth to creation on an unimaginable scale. The immense forces of a galactic collision act like a cosmic hammer, violently compressing these vast clouds of interstellar gas and dust. This compression triggers a ferocious firestorm of new star birth, an event astronomers call a starburst. To understand the sheer power of a starburst, let's travel 60 million light-years away to one of the most famous examples, the antennae galaxies. Here, two spiral galaxies are locked in a slow, grinding collision. From our vantage point, they appear as a tangled mess, with long, flowing tails of stars flung out into space, the antennae that give them their name. But within the chaotic core of this merger, something spectacular is happening. The gas from both galaxies, forced together by gravity, has become a frenzied nursery for new stars. We're not talking about a few stars twinkling into life. In the antennae galaxies, astronomers estimate that hundreds of new star clusters are being born every single million years. Compare that to our own peaceful Milky Way, which might form one or two new star clusters in the same amount of time. The rate of star formation is hundreds, even thousands of times higher. These aren't just ordinary stars either. The conditions are so extreme that they produce what are known as superstar clusters. These are incredibly dense, massive collections of young stars, each containing the mass of millions of suns packed into a region only a few dozen light-years across. They are the titans of the star cluster world, and many astronomers believe these superclusters are the infant versions of the magnificent globular clusters we see orbiting older galaxies. These ancient, glittering balls of stars have long been a mystery, but galactic collisions may provide their origin story. The starburst is essentially forging the future jewels of the galaxy right before our eyes, enriching it with entirely new generations of stars that would never have formed in isolation. The scale of this creative explosion is almost impossible to overstate. Consider a galaxy like M82, another famous starburst galaxy caused by a gravitational tug of war with its neighbor. Its core is a factory of star production, so intense that the combined energy and radiation from all these newborn stars drives a powerful wind, blasting raw material out of the galaxy entirely. It's a system so overwhelmed with star formation that it effectively punches a hole in its own future gas supply. This is the dual nature of the starburst. It is a spectacular, brilliant flash of creation, but it is also incredibly wasteful. A galaxy can only burn so brightly for so long before it consumes the very fuel it needs to keep going. This is how these bursts of star birth ultimately shape the future of the galaxy. They represent a dramatic, accelerated phase of evolution. In a short cosmic time span, just a few 100 million years, a colliding galaxy can churn through its entire reservoir of gas, creating millions of stars in a frantic rush. The largest of these stars live fast and die young, exploding as supernova and seeding the galaxy with heavy elements necessary for planets and, potentially, life. But once the firestorm subsides, the galaxy is often left gas-poor and quiet, having permanently altered its own destiny. The chaotic dance of destruction doesn't just rearrange the stars, it forges new ones and determines the chemical and structural legacy that will last for billions of years. But the creative fury of a starburst is only one side of the coin. The same gravitational chaos that compresses gas to form new stars also performs another, even more dramatic function. It wakes the sleeping giants. At the heart of nearly every large galaxy, including our own, lies a supermassive black hole, a gravitational monster with a mass millions or even billions of times that of our Sun. For most of a galaxy's life, these behemoths are quiet, dormant, essentially invisible because they have little to no material to consume. A galactic collision changes everything, acting as the ultimate dinner bell that summons a feast directly to the black hole's event horizon. This is the fourth shocking revelation. These cosmic crashes don't just build stars, they activate the most powerful engines in the universe. Think of it like this. During a merger, the same tidal forces that create spectacular tidal tails also ruthlessly disrupt the orderly orbits of gas clouds throughout both galaxies. This chaos strips the gas of its angular momentum, its natural tendency to keep circling the center. Without that momentum, vast rivers of gas lose their stability and begin to flow inward, cascading down toward the very core of the galaxy. It's a cosmic-scale plumbing problem where the drain is a supermassive black hole. This incoming deluge of gas doesn't just fall in neatly. It forms a seething, incredibly hot, and bright accretion disk around the black hole, spinning at nearly the speed of light. As the gas is compressed and heated in this disk, just before it crosses the point of no return, it releases a phenomenal amount of energy across the entire electromagnetic spectrum, from radio waves to gamma rays. When this happens, the galaxy's core transforms into what astronomers call an active galactic nucleus, or a GN. In its most extreme and luminous form, it becomes a quasar. A single quasar can so thoroughly outshine every single star in its host galaxy that the galaxy itself becomes a mere wisp of light around a brilliant, point-like beacon. This beacon can be seen clear across the observable universe, making quasars among the most distant objects we can detect. The energy output is almost incomprehensible. A quasar can be thousands of times brighter than an entire galaxy like the Milky Way, all generated from a region of space not much larger than our solar system. This is the incredible power that lies dormant in every galactic center, only unlocked by the violent trigger of a collision. A stunning real-world example of this process unfolding is the galaxy known as NGC 6240. Located about 400 million light-years away, it is the product of two smaller galaxies that are in the late stages of merging. At its heart, astronomers have not found one, but two supermassive black holes. They are separated by a mere 3,000 light-years practically next door in galactic terms, and are swirling around each other in a deadly gravitational dance. Each is likely feeding on the gas driven inward by the merger, making the galactic core a raging inferno of activity. This system gives us a precious glimpse into the future, showing us what happens after the black holes are awakened. Their orbital dance will continue to tighten over millions of years until they finally coalesce into a single, even more massive black hole, an event that will shake the very fabric of space-time itself. This final merger will release a titanic burst of energy in the form of gravitational waves, ripples in the curvature of space-time predicted by Einstein. While we have detected gravitational waves from the mergers of stellar mass black holes, the merger of supermassive black holes will produce waves with wavelengths so long they can only be detected by a future space-based observatory. This will open an entirely new window onto the universe, allowing us to hear the echoes of these cosmic collisions. But the activation of these black holes does more than just create brilliant beacons and gravitational waves. It also gives them a profound regulatory role in the evolution of their host galaxy. The immense energy pouring out from the active nucleus acts as a form of cosmic feedback. It can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars, or it can even drive powerful winds that blow the gas completely out of the galaxy. This process effectively puts a hard limit on how big a galaxy can grow. The black hole, awakened by the very collision that was feeding the galaxy, eventually acts to starve it, quenching further star formation. It's a remarkable self-regulating mechanism. A galaxy cannot grow indefinitely without its central black hole eventually putting on the brakes. This reveals that supermassive black holes are not just passive occupants at the centers of galaxies. They are active participants in a complex dance of creation and destruction, their immense power dictating the life cycle of the very galaxies they call home. So if collisions can birth new stars and awaken black holes, what is the ultimate fate of the galaxies themselves? This brings us to a revelation about identity, a fundamental change that reshapes a galaxy's very essence. We often picture galaxies as majestic, swirling pinwheels like our own Milky Way, with elegant spiral arms tracing paths of star formation. But galactic collisions are the great transformers, the cosmic architects that can completely redesign these structures, often turning a beautiful spiral into something entirely different, a smooth, featureless elliptical galaxy. This morphological shift is one of the most profound and lasting impacts of a merger, rewriting a galaxy's history and its future in one fell swoop. The process is a gravitational masterpiece of chaos and order. A spiral galaxy is a highly organized system. Its stars orbit in a relatively flat, rotating disk, moving in neat, circular paths like cars on a racetrack. This orderly motion is what creates and maintains the iconic spiral structure. But when another galaxy smashes through this disk, it acts like a cannonball through a clockwork mechanism. The immense gravitational forces of the collision violently perturb the orbits of billions of stars, randomizing their paths. The neat, circular motions are thrown into disarray, replaced by orbits that are elongated, tilted, and moving in all different directions. The flat disk is utterly destroyed, and in its place, a new, three-dimensional shape emerges, a football-like or egg-like ellipsoid where stars buzz around in a chaotic, pressure-supported swarm. The galaxy loses its defining features and becomes a smooth, red and yellow haze of old stars. We can witness this dramatic transformation in action by looking at a pair of galaxies known as the Mice, located about 300 million light-years away. Through our telescopes, they appear as two spiral galaxies that have recently undergone a close encounter. Their mutual gravitational pull has already stretched them into spectacularly long, thin tails of stars and gas, streaming hundreds of thousands of light-years into space. Their once pristine disks are now warped and distorted beyond recognition. Astronomers are confident that the Mice are a snapshot of a future elliptical galaxy in the making. Over the next few 100 million years, the two galaxies will completely coalesce. Their stars will mix and their orbits will randomize further. The tidal tails will eventually fall back or disperse, and all that will be left is a single, puffy, elliptical galaxy, a completely new entity born from the destruction of two old ones. This morphological metamorphosis has a crucial side effect. It effectively starves the galaxy's future. Spiral galaxies are often blue and vibrant because they are rich with the cold gas needed to form new, hot, blue stars. But the merger process that creates an elliptical galaxy is incredibly efficient at quenching this star formation. Much of the gas is either rapidly consumed in a final, intense starburst, blown away by powerful galactic winds, or heated to such extreme temperatures that it can no longer collapse to form new stars. The resulting elliptical galaxy is a gas-poor environment, dominated by older, redder stars with very few young, blue stars being born. It becomes a retirement home for stars, a place where the frenzy of youth has passed and a long, quiet senescence begins. This revelation forces us to look at the night sky with new eyes. Every smooth, fuzzy patch of light we see through a telescope, every featureless elliptical galaxy, is not a boring or simple object. It is a cosmic monument, a fossil record of a violent and dramatic past. That seemingly placid glow is the end result of a titanic collision, a galactic merger that occurred billions of years ago. The diversity of galaxy shapes we observe today, the elegant spirals, the bland ellipticals, and the strange irregulars in between, is not a static gallery. It is a dynamic family tree, a direct result of merger history. A galaxy's morphology tells the story of its past interactions, a history of violence and peace that determines its present state and its ultimate destiny. While the transformation of spiral galaxies into ellipticals shows the grand architectural redesign of a collision, the process also creates some of the most breathtaking and delicate structures in the entire cosmos. As two galaxies tangle in their gravitational dance, they don't just merge into a blur, they fling out immense, graceful arcs of material into the intergalactic void. These are tidal tails and bridges, the stunning signatures of a recent encounter, and they act as a forensic roadmap for astronomers to decipher the entire history of the event. It's as if the universe itself is drawing a diagram in the sky to explain the forces at work. To grasp the sheer scale of these features, consider that a single tidal tail can easily stretch for hundreds of thousands of light years. That is a distance far greater than the entire span of the Milky Way galaxy itself. These are not solid structures but rather vast, diffuse streams of stars, gas, and dust that have been gently pulled out from their home galaxies by immense tidal forces, much like the ocean's tides on Earth are pulled by the Moon's gravity. The iconic antennae galaxies, for example, are named for the two long, curving tails that resemble an insect's antennae, each one a monument to the gravitational interaction that is currently shredding the two spirals. These features are ephemeral on cosmic timescales, lasting only a few 100 million years before they either fall back into the merged galaxy or dissipate entirely, making them a clear signpost of a recent and ongoing collision. But these tails are far more than just pretty ornaments. They are active and fertile regions for new creation. The same gravitational forces that pull the material out can also compress the gas within these streams, triggering the formation of new star clusters. In the tidal tails of many interacting galaxies, we see the brilliant blue glow of these stellar nurseries, entire generations of stars being born far away from the chaotic core of the merger. In some extraordinary cases, if a tidal tail contains enough gas and dark matter, it can even collapse under its own gravity to form entirely new, independent dwarf galaxies. This means a galactic collision can actually give birth to new galaxies even as the original ones are being destroyed, a truly poetic cycle of death and rebirth on an epic scale. Beyond the majestic tails, collisions can also forge brilliant bridges of material that directly connect the two interacting galaxies. These are not just visual lines, they are literal highways of gas and stars flowing from one galaxy to the other. This transferred material can provide a crucial infusion of fresh fuel to a galaxy, potentially restarting star formation or even feeding a central black hole. By carefully studying the anatomy of these bridges, their length, density, and curvature, astronomers can work backwards like cosmic detectives. They can determine the precise angles of the galaxy's approach, their relative speeds, and even estimate how long ago the initial encounter occurred. Each tidal feature is a frozen moment in a slow-motion ballet, allowing us to reconstruct a billion-year story from a single, beautiful snapshot. Yet within this grand rearrangement of stars and the awakening of black holes, there's an even more fundamental physical process at work, one that operates on the smallest scales to produce the largest effects. This is the seventh shocking revelation, a phenomenon that acts as the crucial link between the chaos of impact and the birth of new suns. When two galaxies collide, their immense clouds of interstellar gas don't simply pass through one another like the stars or the dark matter. They are tangible, they have substance, and when they meet, they slam together with unimaginable force. This direct, violent contact generates immense shock waves that rip through the galactic environment, and it is within these propagating fronts of energy that the universe's most efficient star-forging mechanism is found. To understand the sheer power of these shock waves, imagine the difference between gently squeezing a handful of snow to make a snowball and compressing air in a diesel engine. One is slow and gradual, the other is a sudden, violent shock that drastically changes the material state. In the vast, diffuse clouds of interstellar gas, gravity alone can slowly pull material together to form stars, but it's a sluggish, inefficient process. A galactic collision provides the cosmic equivalent of a piston slam. It sends a supersonic jolt of energy through the gas, compressing it by orders of magnitude in an instant. This violent compression is so effective that it can force pockets of gas to cross a critical threshold of density, causing them to collapse under their own gravity and ignite into new stars at a ferocious rate that utterly dwarfs anything possible in a quiet galaxy. Some of the most compelling evidence for this violent process comes from a bizarre and wonderfully named system, the Taffy galaxies. This pair, located about 60 million light-years away, recently experienced a high-speed, head-on collision. Unlike other mergers where galaxies might pass through each other and swing back around, the Taffy galaxies appear to have slammed together and stuck like two balls of cosmic taffy. What makes them truly extraordinary is the radio emissions that reveal a vast, turbulent bridge of gas stretched between them. This gas is not quietly sitting there. It is a roiling, chaotic mess, heated and energized by the direct collision between the two galaxies' interstellar mediums. The radio waves we detect are the signature of this colossal impact, a direct snapshot of the immense kinetic energy of the collision being converted into turbulent motion and heat, providing a clear and audible signal of the violence required to trigger star formation. The energy involved in these events is almost beyond comprehension. The shock waves generated can heat enormous volumes of gas to temperatures of millions of degrees. At these extremes, the gas doesn't glow with visible light. It shrieks its presence in high-energy X-rays, which space-based telescopes like Chandra can detect. This creates a fascinating duality within colliding galaxies. Regions of cold, dense gas collapsing to form new stars right alongside vast, diffuse halos of gas that are so hot they could evaporate entire solar systems. This hot gas creates a harsh, high-energy environment that can influence the evolution of the entire galaxy, potentially sterilizing some regions while fueling frantic activity in others. It's a galactic climate system dictated entirely by the after-effects of the collision. This entire process is a spectacular demonstration of energy conversion on a cosmic scale. The kinetic energy of the galaxy's motion, the sheer momentum of their billion-year dance, is not lost. Instead, it is transferred and transformed. It becomes the thermal energy that heats the gas, the turbulent energy that churns it, and most importantly, the compressive energy that overcomes the gas's internal pressure to forge new stars. It's a reminder that in the apparent chaos of a galactic wreck, there is a deep, underlying physics at work, a set of rules that turns destruction into creation with breathtaking efficiency. The shock waves are the universe's tool for ensuring that even the most catastrophic events are not wasted, but are instead harnessed to build the next generation of cosmic structures. While the immense gravitational forces of a collision are busy rearranging stars and compressing gas, another, more subtle power is also being amplified in the chaos, one that is invisible to our eyes but fundamental to the cosmos. This is the eighth shocking revelation. These cosmic encounters don't just play with gravity, they supercharge magnetism. Galactic collisions can take the faint, diffuse magnetic fields that thread through all galaxies and turbocharge them, amplifying their strength and ordering their structure in ways that profoundly influence the entire outcome of the merger. It adds a powerful electromagnetic dimension to what we once thought was purely a gravitational drama. To understand how this works, think of the magnetic field within a quiet, isolated galaxy like the Milky Way. It's a vast, invisible web, incredibly weak by earthly standards, millions of times weaker than a common refrigerator magnet. This field is woven through the space between the stars, often tangled and disordered. But during a collision, this delicate web is thrown into a cosmic blender. The immense turbulence and violent compression that define a merger don't just affect gas and stars, they also stretch, twist, and fold the magnetic field lines themselves. This dynamic process, known as dynamo action, can take that weak, disorganized field and dramatically amplify it, creating a stronger, more organized magnetic structure that can now play a leading role in the galactic evolution unfolding. We can see this spectacular magnetic sculpting in action in one of our favorite examples, the antennae galaxies, also known as NGC 4038 and 39. Radio telescope observations have revealed something astonishing. Along the magnificent tidal tails that stream away from the colliding pair, the magnetic field is not a chaotic mess. Instead, it has become highly ordered, aligning itself neatly along the entire incredible length of these stellar streams. It's as if the gravitational violence of the collision has combed the magnetic field into a smooth, coherent pattern, creating vast magnetic highways that stretch hundreds of thousands of light-years into intergalactic space. This ordering is a direct result of the material being stretched out. As the gas and stars are pulled into these long tails, the magnetic field lines are pulled along with them, forced into alignment. These amplified and ordered magnetic fields are far from passive spectators. They become active players in the collision's aftermath. They act as cosmic guides, influencing how gas flows and where it accumulates. The field lines can provide a scaffold that supports gas clouds against collapse or, conversely, channel flows of material toward regions where new stars are likely to form. They also play a crucial role in the journey of cosmic rays, high-energy particles accelerated by supernova explosions and active black holes. The magnetic fields act like the rails of a particle accelerator, trapping these rays and guiding them along their length, preventing them from simply scattering randomly into the void. This means the magnetic architecture of a merged galaxy can dictate where energy is distributed, effectively shaping the ecosystem of the entire system. The implications of this magnetic enhancement ripple through the entire life cycle of the collision. A stronger magnetic field can increase the pressure within clouds of interstellar gas, making them more resistant to gravitational collapse. This could potentially put a brake on the ferocious starbursts we see, adding a regulating effect that competes with the compressive forces of the shock waves. In this way, magnetism might be one of the factors that determines just how extreme a starburst becomes, acting as a balancing force in the chaotic environment. Conversely, these magnetic fields can also help stabilize the incredible outflows of material, the galactic winds, that are driven by starbursts and active black holes. helping to collimate them into focused jets that can travel far greater distances. This revelation forces astronomers to add a new layer of complexity to their simulations of galactic collisions. For a long time, models focused almost exclusively on gravity and gas dynamics. But now, to truly predict how a merger will unfold, we must also account for the evolving magnetic landscape. The interplay between gravity's relentless pull and magnetism's guiding influence is a delicate dance that can determine the final structure of the merged galaxy, the efficiency of its star formation, and even the activity of its central black hole. It shows us that to ignore magnetism is to miss a fundamental chapter in the story of how galaxies interact, evolve, and ultimately define their place in the universe. But the incredible burst of star formation and black hole activity ignited by a collision doesn't just light up the galaxy, it can also blow it apart from the inside out. This is the ninth shocking revelation, a process of cosmic feedback where the very engines of creation generate powerful winds so immense they can eject the galaxy's future building blocks into the vast emptiness between galaxies. These are not gentle breezes, they are hurricane-force outflows of superheated gas and charged particles, moving at thousands of kilometers per second, and they fundamentally reshape not only their home galaxy but the entire intergalactic environment around it. To grasp the sheer power of a galactic wind, we need look no further than a nearby cosmic powerhouse known as Messier 82 or M82. This is a classic starburst galaxy, its core frenzied with the birth of massive new stars, and it serves as a perfect natural laboratory. When we point our telescopes at it, we don't just see a disk of stars, we see something far more dramatic. Erupting from its central regions, perpendicular to its disk, are colossal plumes of glowing gas, stretching tens of thousands of light years into space. This is the galactic wind in all its visible glory, a titanic geyser of material that is being physically blasted out of the galaxy itself. The driving force behind this exodus is the combined fury of the starburst. Thousands of supernova explosions and the intense radiation from massive young stars act like a cosmic pressure washer, heating the surrounding gas to extreme temperatures and driving it outward with unimaginable force. This process acts as a crucial self-regulating mechanism, a form of galactic feedback. The intense starburst that creates the wind is ultimately consuming the galaxy's reservoir of cold gas, the very fuel needed to make new stars. The wind then ensures this fuel shortage becomes permanent by violently expelling a significant portion of the remaining gas, both processed and unprocessed, far out into the circumgalactic medium. It's as if the galaxy is slamming on its own brakes, quenching its own star formation to prevent a brief, brilliant firestorm from burning out of control. This feedback loop ensures that a galaxy cannot form stars indefinitely at such a ferocious rate. It will eventually run out of fuel, and the wind is the mechanism that helps guarantee it. The impact of these winds extends far beyond simply turning off the star-forming lights. As they surge out of the galaxy, they carry with them a vital cargo, heavy elements. These elements, forged in the nuclear furnaces of massive stars and scattered by their supernova deaths, are the very building blocks of planets, rocks, and life itself. A galactic wind takes these precious materials and, rather than letting them recycle into new stars within the galaxy, hurls them deep into intergalactic space. This is how galaxies enrich their surroundings, seeding the vast, once pristine voids between galaxies with the metals necessary for future generations of stars and planets. It means the atoms that make up our solar system may have originally been blown out of a galaxy like M82 in the distant past, traveling across millions of light years before becoming part of our own cosmic story. The reach of these winds is truly intergalactic in scale. In dense environments like galaxy clusters, the combined winds from many merging and starbursting galaxies can collectively heat the thin gas that permeates the entire cluster. This prevents the gas from cooling and falling back into the galaxies, effectively regulating star formation across the entire cluster and influencing its evolution for billions of years. The wind from a single collision can therefore have a domino effect, its influence rippling outward to impact the ecology of hundreds or even thousands of other galaxies. It's a stunning demonstration that no galaxy is an island. The most violent events within them can dictate the conditions for an entire community of galaxies, linking their fates together across the cosmic web. Yet for all the fury of galactic winds and the brilliance of quasars, there is another, even more extreme class of object born from these cosmic collisions, one that shines not in the light we can see, but in a hidden thermal glow that reveals the true, staggering energy being produced. This brings us to our 10th shocking revelation, the creation of ultra-luminous infrared galaxies, or ULURG. These are the universe's hidden powerhouses, celestial engines so shrouded in the dust of their own violent creation that they become virtually invisible in ordinary light, only to reveal their incredible power when we look at them through the infrared eyes of our most advanced telescopes. To understand why a ULURG is so special, we need to step into the chaotic heart of a major galactic merger. Imagine the incredible starbursts and active black holes we've discussed, but now picture them occurring inside a galaxy that has effectively turned itself into a cosmic blast furnace. The collision itself has churned up all the vast clouds of gas and dust from both galaxies, and the ensuing frenzy of star formation produces massive, short-lived stars that die as supernova, further polluting the environment with even more dust. This creates an incredibly thick, opaque shroud that envelops the entire galactic core. The phenomenal amount of visible light and ultraviolet radiation produced by the billions of new stars and the active nucleus cannot escape. Instead, it is absorbed by this surrounding blanket of dust, but energy cannot simply disappear. The dust particles, having absorbed that immense radiation, heat up to temperatures of tens or even hundreds of degrees, and they begin to re-radiate all that captured energy. But they don't re-radiate it as visible light. They glow with a fierce thermal heat that we see as infrared light. This is why a ULURG is so astonishingly luminous in the infrared part of the spectrum. It is essentially a brilliant cosmic engine that has been wrapped in a thick blanket, where all the furious activity inside is converted into a pervasive, warm glow that leaks out across the entire universe. In many cases, an ULURG can emit over 99% of its total energy as infrared radiation, shining thousands of times brighter in this hidden light than our entire Milky Way does across all wavelengths. A prime example of this phenomenon is sitting relatively nearby, astronomically speaking. ARP 220, located about 250 million light-years away, is the closest ultra-luminous infrared galaxy to us and serves as the archetype for this entire class. It is the result of a head-on collision between two spiral galaxies that are now in the final, violent stages of merging. To our optical telescopes, ARP 220 looks like a messy, distorted blob. But when we point the infrared Spitzer space telescope or the Webb telescope at it, its true nature is revealed. It is an absolute monster of energy production, blazing with the luminosity of over 1 trillion suns, almost all of it in the infrared. Its core is a densely packed region of unimaginable activity, hosting a colossal starburst and at least 2 active supermassive black holes, all hidden from our direct view by walls of dust so thick that not a single photon of visible light can penetrate them. This incredible phase of a galaxy's life is not just a curiosity, it is a critical transitional period. Astronomers now believe that ULRG represent a brief but essential stage in galactic evolution. They are the missing link between a gas-rich spiral galaxy merger and its final fate as an elliptical galaxy or a powerful quasar. The merger provides the fuel, the collision triggers the activity, and the dust shroud hides the messy details of the transformation. Over time, the intense galactic winds driven by the starburst and the active black holes will eventually blow away the dusty blanket that surrounds the galaxy, clearing the stage. Once the veil is lifted, what remains could be a brilliant, unobscured quasar if the black hole is still actively feeding, or a quiet, red and dead elliptical galaxy if the winds have expelled all the remaining gas and quenched star formation forever. This transformative role makes ULRG incredibly valuable beacons for understanding the history of our universe. Because they are so phenomenally bright in the infrared, we can detect them at truly colossal distances, meaning we are seeing them as they were when the universe was much younger. The early universe was a far more crowded and violent place, with galaxies closer together and collisions happening much more frequently. Many astronomers think that the majority of massive galaxies in the early universe went through a ULRG phase as they grew through repeated mergers. By studying nearby examples like ARP 220 in exquisite detail, we are essentially looking back in time, developing a recipe book for how the most massive galaxies in the cosmos were assembled billions of years ago. They teach us that the universe's most dramatic growth spurts were not quiet affairs. They were dusty, hidden, violent events of breathtaking power, whose final products are the majestic galaxies we see in the mature universe today. And now we arrive at one of the most profound and elusive consequences of these cosmic encounters, a finale so immense it warps the very fabric of reality itself. We've seen how collisions trigger starbursts and awaken black holes, but what happens when two galaxies, each with its own awakened supermassive black hole, finally complete their merger? This sets the stage for an even more incredible event, the slow, patient, and ultimately cataclysmic dance of two gravitational titans as they spiral toward a final union. This is the 11th shocking revelation, a process that unfolds over timescales almost impossible to comprehend and culminates in the single most energetic event since the Big Bang, the merger of two supermassive black holes, an event that will literally be felt across the cosmos not as light, but as a vibration in space-time. Imagine the scene: two galaxies have completed their merger, their stars have been thoroughly mixed, their gas has been either consumed or expelled, and a new, larger elliptical galaxy has settled into a stable shape. But at its very heart, a final act of the drama remains unfinished. The two supermassive black holes, which were once the centers of their respective galaxies, now find themselves trapped in a mutual orbit at the core of this new galactic city. They begin a gravitational waltz, circling each other across a distance of perhaps just a few light years. But this is not a vacuum. The core is still populated with stars and the remnants of gas. As the black holes swing around each other, they interact with this environment in fascinating ways that dictate the pace of their final approach. This journey toward merger is not a swift one. It can take hundreds of millions of years and is fraught with potential stalls. The initial stage, where the black holes sink to the center and form a binary pair, is relatively swift, driven by a process known as dynamical friction. As the black holes move through the dense stellar environment, their immense gravity pulls on surrounding stars, creating a gravitational wake that acts like a drag, sapping their orbital energy and causing them to spiral inward. However, once they get within about a parsec of each other, At distance where their gravitational influence becomes dominant, this process becomes less efficient. They have effectively cleared out their immediate neighborhood of stars, and the dance can stall. For the black holes to get any closer, they need to shed more orbital energy, and this is where the true cosmic engineering begins. Several fascinating mechanisms can take over to seal their fate. If there is any residual gas left in the nucleus, it can play a crucial role. The black holes can torque with gas, creating spiral density waves that act like brakes, extracting energy and angular momentum from the binary and allowing it to tighten further. In other scenarios, the gravitational interactions with individual stars become key. A star can make a close pass by the binary black hole system. The complex three-body interaction that follows can fling the star away at high speed, while in exchange, the binary black hole loses a tiny amount of its own orbital energy, drawing the two giants imperceptibly closer. It's a painstakingly slow process of gravitational negotiation, where the black holes pay for their final embrace with the kinetic energy of ejected stars. Eventually, after millions of years of this slow decay, the black holes close the gap to a point where their gravitational bond becomes so strong that they can finally begin to lose energy directly through the emission of gravitational waves. These are the ripples in spacetime predicted by Einstein, generated by accelerating masses. As the black holes orbit each other at a significant fraction of the speed of light in these final stages, they churn the spacetime around them like the paddles of a cosmic mixer, radiating away energy in the form of these waves. This causes their orbit to shrink ever faster, leading to a final, rapid inspiral, a last few furious orbits, and then the merger itself, a violent event where two become one, and a new, more massive black hole is born. The energy released in this final merger is almost beyond imagination. For a brief moment, the power output in gravitational waves can exceed the combined light of every star in every galaxy in the observable universe. It is the most powerful event since the universe began, and yet from our perspective, it is almost completely silent. Unlike a supernova or a quasar, this incredible release of energy does not produce a brilliant flash of light or a torrent of radiation. It produces a tremor in the cosmic fabric, a vibration that propagates outward at the speed of light, stretching and squeezing everything in its path. Detecting this signal requires a completely new kind of astronomy. This is why projects like the Laser Interferometer Space Antenna, or LISA, are so revolutionary. This planned space-based observatory will consist of 3 spacecraft flying in a giant triangle, millions of kilometers apart, using lasers to measure their separation with incredible precision. It is designed to detect the low-frequency gravitational waves produced by these supermassive black hole mergers, while ground-based detectors like LIGO have heard the chirps of stellar mass black holes merging. The collisions of their supermassive cousins produce waves with wavelengths so long they can only be sensed from space. LISA will open an entirely new window on the universe, allowing us to literally listen to the hum of these cosmic collisions, a background symphony of mergers that have occurred throughout cosmic history, and finally witness the silent, universe-shaking finales to the galactic dances we see beginning all around us. While the merging of supermassive black holes represents the grand finale of a galactic collision, the entire structure of the galaxy undergoes a profound and lasting transformation long before that final act. This brings us to a revelation that strikes at the very heart of a galaxy's identity, its spin. A galaxy's rotation is its foundational rhythm, the organized motion that gives a spiral its beautiful structure and defines its character. But a major collision is the ultimate disruptor of this cosmic dance, capable of completely rewriting a galaxy's rotational script. scrambling its orderly motions into a chaotic jumble that forever alters its destiny. To appreciate the sheer scale of this disruption, picture a serene, spinning spiral galaxy. Its billions of stars orbit the center in a coordinated, disk-like pattern, much like a well-choreographed ballet. This orderly rotation is a product of the galaxy's angular momentum, a conserved quantity that keeps the entire system spinning in a stable, predictable way. Now imagine another galaxy plowing through this disk at a skewed angle. The gravitational shock waves from this encounter are catastrophic for this delicate balance. The intruder's gravity doesn't just pull, it torques. It acts like a giant hand reaching into the clockwork, violently transferring and redistributing angular momentum throughout the system. Stars are yanked from their neat circular orbits and sent careening onto new, highly elliptical paths. The entire galaxy can be sent wobbling, its stable axis of rotation tilted or even completely overturned. In the aftermath, the once orderly disk is left with a profoundly altered and often deeply confused sense of rotation. Some of the most stunning evidence for this kinematic chaos can be found in galaxies that seem to be spinning in two directions at once. A perfect example is the lenticular galaxy NGC 4550. At first glance, it looks like a fairly normal, smooth, disk-dominated galaxy. But when astronomers studied the motions of its stars in detail, they uncovered something astonishing. Roughly half of the stars in its disk are orbiting in one direction, while the other half are orbiting in the exact opposite direction. They are quite literally counter-rotating. This is the unmistakable signature of a major past acquisition event. The most likely explanation is that NGC 4550 absorbed a smaller galaxy that was rotating in the opposite direction. Instead of the two sets of stars canceling each other out, they settled into a stable, if bizarre, configuration where they coexist, orbiting past each other in a perpetual cosmic standoff. It's a fossilized record of a past merger, written in the motions of stars for astronomers to decode. This randomization of stellar motions is not just a curious oddity. It is the fundamental mechanism that drives the largest-scale morphological change in the universe, the transformation of spirals into ellipticals. A spiral galaxy is a rotation-supported system. Its flat, disc-eye shape is maintained because the stars are all moving in the same general direction on ordered orbits. A major collision destroys this support system by randomizing the orbits, making some stars orbit clockwise, others counterclockwise, and sending many on steep, plunging trajectories. The galaxy loses its flat structure. The stars begin to move in every possible direction, and it is this random motion that provides the pressure that holds the galaxy up against gravity. The end result is no longer a thin disk, but a puffy, three-dimensional swarm of stars, a pressure-supported elliptical galaxy. The collision has effectively erased the galaxy's past and given it an entirely new identity. The long-term stability of these newly scrambled systems is a complex puzzle. A galaxy like NGC 4550, with its perfectly balanced counter-rotating disks, represents a rare and seemingly stable outcome. But for many merged galaxies, the new configuration can lead to ongoing instabilities. Regions of stars moving in opposing directions can create shear forces, much like weather systems on Earth with winds moving in different directions. This can influence where new stars can form or how gas settles. Furthermore, this altered kinematic state dictates how the galaxy will interact with its future environment. A pressure-supported elliptical galaxy, with its stars on random orbits, is far more resilient to future gravitational encounters than a delicate, rotating spiral disk. It's a classic case of what doesn't kill you makes you stronger. The violent collision that scrambled its rotation also made it more robust and less susceptible to disruption from future flybys or minor mergers, effectively hardening it against the chaos of the cosmic environment. But the gravitational upheaval of a collision does far more than just jumble the orbits of stars. It sends a seismic shockwave directly into the very heart of the galaxy, supercharging its core into a powerhouse of high-energy physics that can outshine the rest of the galaxy combined. This is the 13th shocking revelation, the dramatic enhancement of nuclear activity. While we've seen how mergers awaken supermassive black holes, their influence extends even further, igniting a ferocious inferno of nuclear starbursts and unleashing torrents of the most energetic radiation the universe can produce, transforming these colliding giants into multi-messenger beacons that broadcast their violence across the entire spectrum of physics. At the core of this frenzy is a simple, brutal principle. The collision acts as a cosmic funnel, ruthlessly driving vast quantities of gas and dust down toward the galactic center. This isn't a gentle trickle, it's a catastrophic flood. This sudden, massive infusion of fuel has two simultaneous and spectacular effects. First, it feeds the supermassive black hole, potentially turning it into a brilliant quasar. But second, and just as importantly, it piles up in the dense central regions of the galaxy itself, creating conditions so extreme that it triggers a nuclear starburst, a concentrated firestorm of star formation right in the galaxy's core. This means the very center of the galaxy becomes a dual engine of destruction and creation, a voracious black hole surrounded by a dazzling, dense cluster of millions of the newest, hottest, and most massive stars being born at a frantic pace. The energy output from this double-barreled engine is staggering, and it manifests in ways that push the limits of physics. The intense radiation from the starburst's massive young stars and the searing heat of the black hole's accretion disk work together to create an environment unlike any other. They can accelerate subatomic particles to nearly the speed of light, generating blizzards of cosmic rays. They can produce incredibly high-energy gamma rays, the most energetic form of light, through particle collisions and radiation. In the most extreme environments near the black hole's powerful jets, they might even be responsible for creating neutrinos, elusive, nearly massless particles that travel across the universe almost completely unaffected by matter. This makes a merging galaxy a true multi-messenger source. It doesn't just emit light, it broadcasts information through multiple different cosmic messengers, each requiring a different kind of telescope to detect and each telling a unique part of the story. We don't have to look to a major merger to see this process in action. A fascinating and nearby example is the galaxy known as NGC 1068, also called Messier 77. While it is a spiral galaxy showing clear signs of a past gravitational interaction with a companion rather than a full-blown collision, that encounter was enough to disturb its gas and send a significant amount flowing toward its center. The result is a brilliantly active galactic nucleus, one of the closest and most studied to Earth. Its core is hidden behind a thick, dusty donut-shaped structure, but within that veil, a supermassive black hole is feeding, and the surrounding regions are bursting with star formation. NGC 1068 is so active that it is one of the brightest galaxies in the sky when observed in certain radio wavelengths, and it has been detected emitting high-energy gamma rays and is even a suspected source of neutrinos. It serves as a perfect preview, a scaled-down version of the incredible particle accelerators that full galaxy mergers become. This transformation of a galactic core into a high-energy physics laboratory has profound and far-reaching consequences for the entire galactic ecosystem. The torrent of radiation and particles pouring out from the nucleus doesn't just stay put. it floods outwards, impacting the galaxy on a monumental scale. The intense ultraviolet and X-ray radiation can ionize vast clouds of gas far from the core, effectively sterilizing regions of the galaxy by breaking apart molecules and preventing new stars from forming. The cosmic rays, threaded by magnetic fields, can add pressure to interstellar gas clouds, either helping them collapse to form new stars or providing enough energy to tear them apart. This creates a complex feedback loop where the very activity that was triggered by the influx of gas eventually works to shut down that same inflow, self-regulating the galaxy's growth. The most dramatic impact comes in the form of galactic winds. The combined energy from the nuclear starburst and the active black hole can heat the gas in the central regions to millions of degrees, causing it to expand rapidly and blow outward in a superwind that races through the galaxy. These winds can carry away millions of solar masses of material, enriching the space between galaxies with heavy elements and effectively shutting down star formation for billions of years. This process links the microscopic physics of particle acceleration in the nucleus to the macroscopic evolution of the entire galaxy, determining whether it will continue to birth new stars or enter a quiet retirement. The enhanced nuclear activity born from a collision doesn't just create a spectacular light show. It writes the final chapter in the galaxy's story of growth, leaving a permanent mark on its structure and its future potential for creation. While the violent chaos of a recent collision paints the cosmos in brilliant bursts of light and energy, the universe also keeps a quieter, more patient record of its past mergers, one that requires a deeper, more subtle look to uncover. This brings us to our 14th shocking revelation, a phenomenon that acts as a cosmic archaeologist, preserving the evidence of ancient encounters not in brilliant starbursts, but in delicate, ghostly ripples. In the halos of many massive elliptical galaxies, astronomers have discovered faint, concentric shell-like structures made of stars, ethereal echoes of a long-ago act of galactic cannibalism that have been frozen in time for billions of years. The formation of these beautiful shells is a masterpiece of gravitational physics. It begins when a large galaxy, often an elliptical, gravitationally captures a much smaller, dwarf galaxy. The tidal forces of the larger galaxy are so immense that they completely tear the smaller one apart, stripping away its stars. But these stars aren't simply absorbed into a smooth blend. Instead, they are flung out into wide orbits around the predator galaxy. Now, here's the crucial part. These orbits aren't random. The stars from the devoured galaxy become organized or phase-wrapped. Imagine swinging a yo-yo in a circle around your hand. If you could freeze its path at different points, you'd see a series of nested loops. The stars from the consumed galaxy behave similarly, their orbits aligning in such a way that when we view them from Earth, we see them pile up at the turning points of their trajectories, creating the illusion of brilliant, sharp-edged shells nested within one another. To witness this phenomenon in its most spectacular form, we can look to the galaxy NGC 3923, a stellar system located about 90 million light-years away. Through long exposure, ultra-deep images, astronomers have counted an astonishing 20 or more of these faint stellar shells enveloping the galaxy's main body. They appear as faint arcs, layered like the rings of a celestial onion, each one marking a different orbital phase of the stars from a single, long-dead satellite galaxy. This isn't evidence of 20 different mergers, but rather 20 different chapters in the story of one single, ancient assimilation event. The sheer number of shells indicates that the merger happened a very long time ago, giving the stars ample time to complete many orbits and create this complex, layered structure. The incredible longevity of these features is what makes them so valuable to science. Unlike the dazzling but short-lived tidal tails that fade after a few 100 million years, these shell structures are incredibly stable and can persist for many billions of years. This means they act as a permanent fossil record, preserving the evidence of a merger that likely occurred when the universe was far younger. By studying the number of shells, their spacing, and their brightness, astronomers can work backwards to determine not just that a merger happened, but also the mass of the galaxy that was consumed, the angle at which it was captured, and even how long ago the event took place. Each set of shells is a time capsule, holding within its delicate structure the entire history of a single, ancient cosmic encounter. This fossil record allows us to answer a fundamental question about the life of a galaxy. How often do these major mergers occur? The prevalence of shell structures in otherwise smooth elliptical galaxies tells a clear story. Cannibalism is not a rare event. It is a standard part of a massive galaxy's growth diet. The fact that we can still see these clear signatures billions of years later suggests that the quiet, featureless ellipticals we see today were built through a steady, hierarchical process of consuming smaller neighbors over cosmic time. The shells of NGC 3923 and countless other galaxies like it are the ultimate proof that the serene appearance of many galaxies is a mask, hiding a violent and dramatic history of repeated collisions that have shaped them into the giants we observe today. But the gravitational turmoil of a collision reaches even into the fine details of a galaxy's architecture, reshaping not just its overall form but its most prominent internal features as well. This brings us to a fascinating revelation about the delicate dynamics within spiral galaxies and the powerful gravitational forces that can either forge or shatter them. At the heart of many spirals, including our own Milky Way, lies a brilliant, elongated structure of stars known as a stellar bar. It acts as a central hub, a rigid bridge of stars that rotates as a single unit. Whether these bars are created, strengthened, or completely demolished by a galactic encounter depends entirely on the precise choreography of the collision, adding yet another layer of intricate detail to how these events unfold. The formation of a stellar bar is a story of gravitational instability and the transfer of angular momentum. In a stable, isolated spiral galaxy, the orbits of stars are generally circular and orderly, maintaining the galaxy's delicate disk structure. However, the gravitational shock of a close encounter with another galaxy can violently disrupt this balance. The intruder's gravity can torque the disk, stealing angular momentum from the inner regions and depositing it in the outer parts. This loss of momentum in the center causes stars there to no longer be able to maintain their circular paths. Their orbits become more elongated, and as more and more stars get pulled into these oval-shaped trajectories, they collectively align to form a rigid, rotating bar that cuts through the galactic center. It's a stunning example of how gravitational chaos can lead to a new, ordered structure. However, the very same process can also work in reverse. If a galaxy already possesses a strong stellar bar, a subsequent collision can be its undoing. A direct head-on encounter or a particularly violent gravitational interaction can inject so much fresh energy and chaos into the system that it completely destroys the delicate orbital resonance that holds the bar together. The stars that once moved in lockstep are scattered onto random paths, and the coherent structure simply dissolves away. Sophisticated computer simulations of galactic collisions show this dual potential beautifully. A slow, grazing encounter might gently torque a disk and spark the birth of a bar, while a more direct, high-speed collision could completely obliterate an existing one. The final outcome is a complex dance dictated by the mass of the intruder, the angle of impact, and the speed of the encounter. Once formed, a bar becomes a powerful engine for driving further evolution within the galaxy. It acts as a cosmic funnel, a gravitational railroad that very efficiently channels gas from the outer disk inward toward the galactic nucleus. This forced migration of cold, dense gas has two dramatic consequences. First, it can pile up in the central regions, creating the conditions for an intense nuclear starburst, lighting up the galaxy's core with the birth of millions of new stars. Second, this river of gas can flow all the way down to the supermassive black hole lurking at the very center, providing it with a sudden feast of fuel that can awaken it from its slumber and ignite a brilliant active galactic nucleus. In this way, a bar instability triggered by a collision can set off a chain reaction of events that fundamentally alters the galaxy's energy output and future development. This dynamic interplay forces astronomers to add yet another variable to their already complex models of galactic evolution. The presence or absence of a bar can dramatically change how a galaxy responds to a merger and what it looks like billions of years later. A galaxy with a strong bar might funnel gas away efficiently, quenching star formation in the disk and creating a red and dead appearance sooner. A galaxy without a bar might retain its gas for longer, allowing for a more extended period of quiet star formation. This means that to truly predict the fate of any given galaxy, we must understand not only its collision history, but also the state of its internal structures before, during, and after the encounter. The humble stellar bar, once just a curious feature in spiral galaxies, is now understood to be a crucial player in the grand cosmic story of how galaxies live and die. While the brilliant starbursts and swirling tidal tails capture our immediate attention during a galactic collision, there is a far more subtle and haunting aftermath to these events, one that lingers for billions of years like a faint cosmic ghost story. This is the production of diffuse light, a phenomenon where the violent gravitational tides of a merger don't just rearrange stars, they completely liberate them, casting them out into the darkness to form a vast, ethereal glow that permeates the spaces between galaxies. This isn't the light of a single galaxy. It is the collective radiance of countless stars that have been utterly lost, stripped from their homes, and left to wander the void as a permanent testament to the violence that created them. To understand how this happens, picture the final, slow-motion act of a galactic merger. As two galaxies intertwine, their mutual gravitational pull creates immense tidal forces that act like cosmic gravity wells. Stars orbiting in the outer regions of each galaxy, where the gravitational grip is weakest, are the most vulnerable. They are not physically torn apart, but they are gravitationally plucked from their orbits and flung out into intergalactic space. Unlike the gas that slams together to form new stars, these orphaned stars are simply set adrift. They are no longer bound to any single galaxy. Instead, they become part of a vast, diffuse cloud that fills the entire galaxy cluster, a sea of stars without a home. This faint illumination is known as intra-cluster light, and it is one of the most challenging and rewarding things for astronomers to study. The key to unlocking its secrets lies in the power of deep, patient observation. In a standard astronomical image of a famous cluster like the Coma cluster, you see the brilliant pinpricks of individual galaxies. But if you take an incredibly long exposure, subtracting the light from those obvious galaxies and the glare from nearby stars, something magical emerges. A faint, soft glow materializes in the spaces between the galaxies. It's not attached to anything, it's just there, a pervasive haze of light that can account for a surprisingly large portion of the cluster's total brightness, in some cases up to 20% or more. This is the intra-cluster light, the combined glow of billions upon billions of solitary suns, each one tracing a lonely path through the dark heart of the cluster. What makes this light so profoundly important is that it acts as a fossil record of a cluster's most violent history. The Coma Cluster, for instance, is a dense collection of over 1,000 galaxies. Its intra-cluster light is not the result of one or two recent mergers. It is the accumulated debris from eons of galactic cannibalism. Each stream of faint starlight represents the final, dissolved remains of a galaxy that was torn apart and absorbed by the cluster's collective gravity long ago. By carefully mapping the distribution and chemistry of this light, astronomers can perform a kind of cosmic archaeology. They can trace the paths of ancient mergers, estimate how many galaxies have been consumed over billions of years, and even determine the types of galaxies that were destroyed, whether they were gas-rich spirals or older, redder ellipticals. This reveals the true hierarchical nature of cosmic structure. Galaxy clusters are not static collections. They are dynamic ecosystems that grow from the bottom up. Smaller groups of galaxies merge to form larger groups, which then fall into and merge with even larger clusters. With each merger event, more stars are stripped away and added to the intra-cluster glow. The diffuse light is therefore a direct measure of the cluster's assembly history. A cluster with a large amount of intra-cluster light is one that has experienced a very violent and active past, full of mergers and acquisitions. A cluster with very little has lived a more quiescent life. By reading this faint, ghostly signature, we can understand not just the history of individual galaxies, but the entire life story of the largest gravitationally bound structures in the universe. But beyond the grand reshaping of structures and the liberation of stars into the ghostly intergalactic haze, a galactic collision orchestrates a more intimate and fundamental transformation, one that occurs at the atomic level and holds profound implications for the very building blocks of life itself. This is the 17th shocking revelation, a process that acts as the universe's ultimate blender, mixing together the distinct chemical compositions of two separate galaxies to create an entirely new cosmic recipe. When galaxies collide, they don't just exchange stars and gas. They pool their elemental histories, altering the distribution of heavy elements, what astronomers call metallicity, and in doing so, they directly influence the potential for future worlds and perhaps future life to emerge. To grasp why this matters, we need to understand that the universe wasn't always rich with the elements that make up our world. In the pristine early universe after the Big Bang, there was only hydrogen, helium, and a trace amount of lithium. Every other element on the periodic table, the carbon in our cells, the oxygen we breathe, the iron in our blood, the silicon in our planet's crust, was forged later in the nuclear furnaces of stars and scattered across space in the violent deaths of supernova. This means that galaxies have a chemical history. Their gas clouds are enriched with these heavy elements over time by successive generations of stars. A galaxy that has undergone many cycles of star formation will be more metal-rich than a young galaxy or a small dwarf galaxy that has seen little star-forming activity. Crucially, this metallicity is not uniform. It often exists in a gradient, with the central regions of a galaxy being more enriched than its outer fringes, a testament to its long and complex history of stellar birth and death. A galactic collision violently disrupts these carefully layered chemical gradients. Imagine two galaxies with different enrichment histories coming together. One might be a large, mature spiral with metal-rich gas, while its companion could be a smaller, more primitive dwarf galaxy with gas that is still relatively pristine. As they merge, their gas clouds don't just pass by each other, they slam together, churn, and mix. The resulting turbulence acts like a giant spoon, stirring these two distinct chemical soups into a single new mixture. This isn't a gentle process, it's a chaotic one that can create wild and unpredictable variations in metallicity throughout the newly forming galaxy. Astronomers can actually trace these flows of material by mapping these chemical variations. Regions with unexpectedly high or low metal content act as signposts, pointing directly to the paths that gas traveled during the merger, allowing us to reconstruct the entire event through its chemical fingerprint. This chemical evolution is far more than a curiosity. It is a fundamental driver of a galaxy's future. The metallicity of a gas cloud is one of the most important factors in determining how stars form. Metal-rich gas cools more efficiently, allowing it to collapse more easily into new stars. It also influences the types of stars that are born. A cloud with higher metallicity is more likely to form smaller, less massive stars that burn for billions of years like our Sun. In contrast, metal-poor environments tend to favor the formation of truly massive, incredibly bright stars that live fast, die young in spectacular supernova, and in turn, enrich their surroundings even further with newly forged heavy elements. A galactic collision, by resetting the metallicity of vast swaths of gas, effectively resets the star formation rulebook for that system, dictating the types of stars that will dominate its next generation and how efficiently they will be born. And this brings us to the most profound implication of all, the direct link to habitability, the elements essential for life as we know it and for the formation of rocky planets are all products of stellar nucleosynthesis. A solar system forms from a collapsing cloud of gas and dust, and the chemical composition of that cloud is inherited by the resulting stars and planets. A protoplanetary disk born from metal-rich gas will have a much greater abundance of the key ingredients carbon, oxygen, nitrogen, iron, silicon necessary to form terrestrial planets with solid cores and complex chemistry. Therefore, a galactic collision, by stirring and enriching the interstellar medium, is not just a constructor of galaxies, it is a prime architect of the very environments where rocky, Earth-like worlds are most likely to form. The cataclysmic dance of two galaxies, which seems so destructive, may in fact be one of the most important mechanisms for seeding the cosmos with the raw materials for planets and life, ensuring that the aftermath of chaos is a future filled with new possibilities. And now we arrive at a prediction so profound it comes directly from Einstein's theory of general relativity, a phenomenon that represents the final, silent whisper of the most violent events in the cosmos. We have witnessed the brilliant light shows, the restructuring of galaxies, and the awakening of black holes, but the grand finale of a supermassive black hole merger doesn't announce itself with a flash of light. Instead, it shakes the very fabric of spacetime itself, sending out ripples that travel across the universe at the speed of light. This is the generation of gravitational waves, a low-frequency hum that is the ultimate signature of these cosmic collisions, and until very recently, it was a part of the universe we were completely deaf to. These are not the high-pitched chirps that ground-based observatories like LIGO and Virgo have detected from merging stellar mass black holes. The merger of supermassive black holes, with masses millions or billions of times that of our Sun, is a much slower, more drawn-out event. Their immense size means they produce gravitational waves with wavelengths so long they are measured in thousands or even millions of kilometers, and frequencies so low that a single wave cycle can take years to complete. These waves are not a sharp signal, they are a deep, resonant thrum, a bass note in the cosmic symphony that is impossible to detect from the surface of our seismically noisy planet. To hear this frequency, we must go to space, where the quiet vastness allows us to listen for the faintest vibrations in the cosmic background. This is the revolutionary goal of missions like the Laser Interferometer Space Antenna, or LISA. Planned for launch in the next decade, LISA will consist of 3 spacecraft flying in a perfect triangular formation, millions of kilometers apart. trailing behind Earth in its orbit around the Sun. By firing lasers between these spacecraft and measuring the infinitesimal changes in the distance between them with breathtaking precision, LISA will act as a giant ear tuned to the low-frequency gravitational wave spectrum. It will be able to detect the change in distance caused by a passing gravitational wave, a shift smaller than the width of a single atom over a span of 1,000,000 kilometers. This will allow us to literally listen to the final moments of two supermassive black holes as they spiral together and merge, hearing the event that our optical telescopes could only infer. The information encoded in these waves is a treasure trove of astrophysical data. The specific pattern of the waves, their changing frequency and amplitude, will tell us the precise masses of the two black holes involved. The subtle details of the signal will reveal their individual spins, whether they were rotating in the same direction as their orbit or were tilted and misaligned. This spin information is a crucial clue, as it acts as a forensic record of the black hole's history. Did they grow steadily by absorbing gas from a consistent direction, leading to aligned, rapid spins, or were their spins scrambled by a chaotic merger history with multiple smaller black holes coming in from random angles? The gravitational wave signal will hold the answers, allowing us to read the life story of these enigmatic objects written in the ripples of space-time. But perhaps the most exciting prospect is not just hearing individual mergers, but listening to the collective chorus of them all. Throughout cosmic history, countless galaxies have merged and countless supermassive black hole pairs have coalesced. Each one contributed its own gravitational wave signal. While the individual events have faded, their combined emissions have created a persistent, overlapping background hum that fills the entire universe. This stochastic gravitational wave background is like the faint static of a detuned radio, a noise that is actually the sum of every supermassive black hole merger that has ever occurred. Detecting this background will allow us to take a census of black holes across time and space, providing a completely new way to measure how often these colossal mergers happen and how the population of supermassive black holes has evolved over the last 13 billion years. It will open an entirely new window onto the universe, one that is complementary to light, allowing us to hear the hidden history of cosmic structure being built through collision and merger. While the titanic collision between the Milky Way and Andromeda will dominate the cosmic headlines billions of years from now, this event is not an isolated duel between two giants. Both of our galaxies travel with immense entourages, vast clouds of smaller satellite galaxies that orbit them like moons around a planet. The 19th revelation shows us that the fate of these smaller systems is inextricably tied to the dance of their giant hosts. When large galaxies collide, they don't just reshape each other. Their gravitational fury sends shockwaves through their entire satellite systems, disrupting orbits, triggering star formation, and often leading to the complete assimilation of these smaller cosmic companions, permanently altering the galactic neighborhood. To visualize this, imagine the serene, orderly orbit of a dwarf galaxy around a large spiral like the Milky Way. It might have been following a stable path for billions of years, its own star formation and internal dynamics governed by its own isolated history. Now, introduce the immense gravitational perturbation of another giant galaxy, Andromeda, plowing through this carefully balanced system. The gravitational shock waves from this encounter are catastrophic for the satellites. Their stable orbits are violently disrupted. Some may be flung outward on new, hyperbolic trajectories, ejected from the galactic group entirely to wander the void as isolated orphans. Others might have their orbits drastically altered, sent plunging on a new, doomed path that takes them directly through the chaotic heart of the merging giants. This gravitational chaos doesn't just change their paths, it can fundamentally alter their very structure and star-forming lives. A satellite galaxy that finds itself on a new, plunging orbit can experience a dramatic and final chapter. As it dives through the diffuse outer halo of its host galaxy, it can experience ram pressure, a force similar to the wind you feel against your hand when stuck out of a moving car window, but on a cosmic scale. This can strip away its precious reservoirs of gas, the raw material for future stars. Even more destructive are the tidal forces. The difference in gravitational pull from the host galaxy between the near and far side of the satellite can stretch and distort it, pulling out streams of stars and gas in a process called tidal shredding. For many dwarf galaxies, a close passage during the merger will be a death sentence, their stars slowly but surely being added to the diffuse halo of the larger galaxy, their identity erased forever in an act of hierarchical consumption. We can see a preview of this fate playing out right now in our own cosmic backyard. The Large and Small Magellanic Clouds, the two most prominent satellite galaxies of the Milky Way, are not on stable, long-term orbits. Observations show they are likely on their first passage around our galaxy, and their close interaction with each other and with us has already triggered intense star formation, such as in the vast Tarantula Nebula. But their future is tied to the larger collision. When the Milky Way and Andromeda begin their merger, the chaotic gravitational environment will almost certainly destabilize the orbits of the Magellanic Clouds and other satellite dwarfs. They will likely be torn apart, their stars absorbed into the new elliptical galaxy that forms, known as Milkomda. They are living on borrowed time, their eventual consumption a foregone conclusion once the larger galactic dance begins. This process of satellite disruption is a key mechanism in what astronomers call hierarchical structure formation, the idea that small structures merge to form larger ones. The satellite populations we see around galaxies today are not the pristine, original set. They are the survivors of a long history of mergers and acquisitions. A galaxy's entourage of dwarfs tells a story of its past interactions. A galaxy that has undergone a recent major merger may have very few satellites left, having consumed them during the event. Another might have a large number of satellites on chaotic, misaligned orbits, a clear sign of a recent gravitational disturbance. By studying the distribution, motions, and even the chemical compositions of these satellite galaxies, we can work backwards to reconstruct the merger history of their host, reading the story of cosmic violence written in the survivors. But what if we step back from the individual drama of these collisions and view them from the grandest possible perspective across the entire lifespan of the universe? This final revelation is perhaps the most profound of all, reframing our entire understanding of cosmic history. We have explored the shock waves, the starbursts, and the black hole mergers, but we must now see them not as isolated catastrophes, but as the fundamental engine of cosmic evolution itself. Galactic collisions are not rare accidents. They are the primary mechanism through which the universe builds its largest structures, forges the elements for life, and sculpts the beautiful diversity of galaxies we see today. This ongoing process of construction and destruction is the very heartbeat of a dynamic cosmos, and it places mergers at the absolute center of the universe's great story. To understand why this is, we must journey back in time close to the beginning of everything. In the early universe after the Big Bang, matter was not neatly packaged into majestic spirals and ellipticals. Instead, it was distributed in a vast cosmic web of dark matter, with ordinary matter following its gravitational pull, condensing into smaller, denser clumps. The first galaxies to form in these dense nodes were tiny, irregular, and chaotic, mere building blocks compared to the giants we see today. Isolated, these primordial dwarfs would have remained small, perhaps continuing to form stars at a sluggish pace for eons. But the universe is not static. Gravity is a patient and relentless force. These small proto-galaxies, drawn together by their mutual attraction, began to merge. This was the inception of a process that would continue for billions of years, hierarchical structure formation, where small structures consistently merge to form larger and larger ones. This is why astronomers are now certain that most, if not all, massive galaxies have a history steeped in violence. Our own Milky Way is a perfect example. By studying the motions and chemical compositions of stars in its halo, we have found the ghostly remnants of dozens of smaller galaxies it has already consumed. It is a galactic cannibal with a rich history of mergers, each one adding to its mass and altering its structure, and this is not a unique fate. The majestic Andromeda galaxy shows similar signs of a violent past. The giant elliptical galaxies that sit at the hearts of dense clusters are the ultimate products of this process, likely having undergone multiple major mergers that erased their disks and randomized the orbits of their stars. Without this relentless cycle of collision and assimilation, the universe would be a very different place, populated mostly by small, faint, and undeveloped galaxies. The magnificent giants that dominate our night sky simply would not exist. The implications of this extend far beyond simply making galaxies bigger. These collisions are the universe's primary tool for driving change and innovation. They are the catalysts that force galaxies to evolve. A quiet, isolated spiral galaxy can continue on a steady, uneventful path for billions of years. But a merger disrupts this stagnation. It triggers the intense starbursts that forge heavy elements and enriches the galactic environment. It funnels gas to central black holes, regulating future growth. It transforms structures, creating the diversity of forms we see in galaxy surveys. Essentially, collisions prevent the universe from becoming a boring, static place. They introduce chaos, and from that chaos emerges a new order, a new generation of stars and new possibilities. Most profoundly, this process is directly responsible for our own existence. The heavy elements necessary for life, the oxygen, carbon, iron, and nitrogen that make up our bodies and our planet, are created in the hearts of stars and scattered by their explosive deaths. But in a small, quiet galaxy, this process of chemical enrichment is slow and inefficient. It is the immense collision-induced starbursts that act as cosmic factories, producing these elements in enormous quantities and seeding the interstellar medium with the raw materials for planets and biology. The very atoms that constitute Earth and every living thing upon it were likely forged in the brilliant, short-lived firestorm of a galactic merger that occurred billions of years before our solar system was even a cloud of gas and dust. Our cosmic history is written in these violent encounters. We are quite literally the children of galactic collisions. So, how do these events fit into the broader timeline of the universe? They are the defining narrative of its middle age. In the youth of the cosmos, mergers were far more frequent and violent, as the universe was smaller and denser. This is the era when the most massive ellipticals were assembled. As the universe continues to expand and galaxies move farther apart, the rate of major mergers will gradually decline. The future will be dominated by the slow consumption of dwarf satellites and the eventual, inevitable collision of our local galactic group. The story of the universe is thus a story of assembly, a gradual building up from tiny seeds to the grand structures we see today, all orchestrated by the relentless, creative, and destructive force of gravity, making collisions the most important chapter in the biography of our cosmos. From triggering colossal starbursts that forge new suns to the silent, space-time shaking mergers of supermassive black holes. These 20 revelations paint a universe where creation and destruction are two sides of the same cosmic coin. We've journeyed through a reality where galaxies are not isolated islands but dynamic participants in a slow, gravitational dance that builds, transforms, and ultimately defines the cosmos. Each discovery peels back a layer, revealing that these events are not simple crashes but intricate, creative engines that drive the evolution of everything we see. They challenge our most fundamental understandings, forcing us to see the universe not as a static painting, but as a living, breathing, and ever-changing entity, where chaos is the necessary precursor to new order. As we stand on the precipice of a new era in astronomy, the future promises to unveil even deeper layers of this cosmic story. The upcoming launch of the James Webb Space Telescope and the Future Laser Interferometer Space Antenna will act as new sensors for humanity, allowing us to peer further back in time to witness the mergers that built the first galaxies and to literally hear the low-frequency hum of colliding black holes that fills the universe. These advancements will undoubtedly bring revelations even more shocking than the ones we've explored today, perhaps answering the profound questions these collisions raise about the nature of dark matter, the ultimate fate of galaxies, and the intricate feedback loops that govern cosmic evolution. This narrative is not just about distant giants, it is intimately connected to our own existence. The very atoms that make up our planet and our bodies were forged in the hearts of stars born during ancient galactic collisions, scattered across space by supernova explosions, and eventually incorporated into the nebula that gave birth to our solar system. Our cosmic history is written in these violent encounters. We are, in the most literal sense, children of galactic mergers. Reflecting on this, we can look at the night sky not with fear, but with a sense of profound connection to the dynamic processes that made our world possible. And this story has a next chapter, one written in the slow, inevitable motion of our own galactic neighborhood. In about 4.5 billion years, the Milky Way and the Andromeda Galaxy will begin their own majestic, slow-motion collision, an event that will forever alter the night sky for any future inhabitants of Earth. The serene band of our galaxy will be replaced by a dazzling, chaotic tapestry of new stars and swirling gas as the two giants merge into a new, elliptical galaxy some call Milkomda. It's a future that underscores the central theme of our journey. Change is the only constant in the universe, and from the grandest collisions emerge new possibilities, new structures, and new wonders. Thank you for joining us on this incredible voyage through the shocks and wonders of galactic collisions. We've only scratched the surface of this dynamic field, and every answer seems to lead to a dozen new and exciting questions. The universe is a place of endless fascination, and we are just beginning to learn its deepest secrets. If you enjoyed exploring these cosmic encounters with us, please like this video, subscribe to the channel for more journeys into the mysteries of space, and let us know in the comments below which revelation surprised you the most. Until next time, keep looking up.